All right. So hello, my ISL is about paradoxes in relativity. So as an overview, we're going to go over Einstein's theory of relativity, just as a recap, and then we're going to talk about three famous thought experiments: the twin paradox, the Ladder-Barn paradox, and the Einstein-Podolsky-Rosen paradox, or the EPR paradox. And just overall, I'm going to give a more conceptual view of all of these, and we're not really going to go into any of the math involved. So first of all, what is relativity? So relativity is this new way of thinking about physics, this new model of representing reality that Einstein developed. And it's more accurate than traditional Newtonian physics, which had been used up till that point. Newtonian physics is like general high school physics. It's simpler than relativity, and it's very absolute and deterministic, because according to Newtonian physics, the laws of physics are the same no matter how fast you're moving or where you are. All observers will measure the same things. And this works pretty much perfectly for all everyday purposes, like throwing a ball or flying a plane, but it really starts breaking down in two areas: when you move near light speed or in the quantum world, where things get very small. Technically, Newtonian physics isn't ever correct, but in everyday life, the errors are just so small that we don't really care about them. So relativity helps fix the first issue, where it's near light speed. It still doesn't quite work with the quantum world, but we'll get into that later. Also, we're going to focus on special relativity today, not general relativity. So special relativity is based on just two postulates, just two assumptions. The first one is that the laws of physics are the same in all inertial frames of reference. Now, reference frames is a very important piece of vocabulary, and it basically just means any non-accelerating point of view. So, for example, if you're in free fall at terminal velocity, or if you're in a plane flying at constant velocity, or if you're just sitting still, those are all inertial reference frames, since you're not accelerating. Additionally, this basically implies that there's no experiment you could do to determine whether you're moving or not, as long as you're in an inertial reference frame. For example, if you're in a plane, you can only tell you're moving relative to the clouds. All motion is relative. There's no experiment you could do to determine that you were moving in a plane, since the laws of physics work equally in all reference frames. Once you begin to accelerate, though, this starts breaking down, and you can start to tell whether you're accelerating or not. When you're accelerating, you're no longer in an inertial reference frame, and special relativity no longer applies. The second postulate of special relativity is that the speed of light is constant, no matter what reference frame it's measured from. And this has some pretty weird implications, because let's say hypothetically, you were in a car that was traveling at the speed of light, and you turned on the headlights. Would you be able to see the headlights? What would happen? So if you were in the car, from the car's point of view, it's not moving. So it would just see the headlights turn on as normal, and the light would come out at the speed of light. However, if you were watching this car, you wouldn't be able to see anything. You would see the headlights turned on, but no light would come out, because the light would travel at the same speed as the car. Both of these views are equally valid, according to special relativity. Special relativity also implies the existence of these two really weird phenomena, called time dilation and length contraction. So basically what this states is that reference frames which are moving relative to a non-moving frame, they're shorter and they experience time slower. And I don't mean that you perceive them to be shorter. I mean they are literally physically shorter, and time itself slowed down. Biological processes, clocks, radioactive decay, it's all slower. And I think the best way to kind of wrap your head around how this works is with an example, which also helps to serve as proof. And it's the example of muon decay. So some background information. Muons are just particles that are traveling from space to Earth at near light speed. And we can measure their decay time, their lifespan. Theoretically, their lifespan is so short that most of them should decay before they hit Earth. But we can find quite a lot of them on Earth, more than we expected. Why? Well, relativity helps explain this. So let's look at the points of views of both person on Earth and the muons. So if we're just a person on Earth, we aren't moving relative to Earth. The muons are moving relative to us. Since the muons are moving at a constant speed, they're in an inertial reference frame, and they should experience time dilation. They also experience length contraction, but that's not relevant right now. This effectively slows the muons down. It slows down their decay, so they have more time to reach the Earth's surface. However, if we look at this from the muons' point of view, they aren't moving. They don't experience time dilation. Instead, it's the Earth that experiences time dilation. But right now, what's more important is that the Earth also experiences length contraction, which means that to the muons, the Earth is literally squished. There's less space for them to traverse, which means that even with their normal short lifespan, since they have less distance to cover, they can travel that distance, and this allows them to make it to the surface of Earth. As you can see, time dilation and length contraction kind of work together with the two reference frames to make sure that the observations stay consistent. However, things aren't always so clear, and that's where I think we can run into these so-called paradoxes. The first one we're going to look at is the twin paradox. It's pretty famous, I'm sure lots of people have heard of it. But just to be clear, this isn't actually a paradox. There is a resolution, there is a correct answer. It's just a good example of where it's easy to get tripped up with special relativity. So this is the premise of the twin paradox. You have two twins, let's call them Allie and Bob. And let's just suppose that Bob stays on Earth while Allie gets in a spaceship and travels at near light speed somewhere far away and then returns. Who is older when Allie comes back? So here's the paradox. The problem here is that there seems to be a conflict between Allie and Bob's frames of reference. According to Bob, Allie was moving away at near light speed. Therefore, she should experience time dilation and time should move slower for her. Because of this, when she returns, less time should have passed for her and she should be younger. However, Allie can use the exact same reasoning with her reference frame. Since, according to Allie, she was the one who wasn't moving and Bob was the one who was moving away and coming back. Bob should have experienced time dilation and therefore he should be younger. They can't both be younger, so who's right? The short answer here is that when Allie turned around, when she went and then she turned around, she had to accelerate. It might have been for a very short moment, but she still had to accelerate. And remember, special relativity doesn't apply within an accelerating reference frame. Therefore, you can't actually consider the two perspectives as symmetrical. Allie's reasoning can't be the same as Bob's because Allie was in two reference frames, one where she was going away from Earth and one where she was coming back. Therefore, this works out so that Bob was correct. If you want the long answer and the more interesting answer, we should look at a space-time diagram. So a space-time diagram, it's just this little graph over here, and it lets us graph the movement of objects through space-time. And remember, since motion is relative, these are always graphed according to a specific point of view, to a specific reference frame. In this case, we're going to graph it based on Bob's reference. The x-axis shows movement through space, or at least one dimension of space. So technically, a space-time diagram could be four-dimensional, but that's too hard to think about, so we're just going to go with this 2D, one-dimensional space. And the y-axis is movement through time. In our universe, it's impossible to stay in place on this graph since we're always moving through time. Additionally, over here, usually space-time diagrams are scaled so that light hits at a 45-degree angle. So this line right here is just a reference for what light would travel at on the space-time diagram. Here are what's called world lines. So world lines are just kind of the lines that objects trace as they move through space-time. So Bob, in this case, I have graphed in green, and Allie, I have graphed in purple. So Bob doesn't move in his, again, this is from his reference frame, and so he doesn't move. He stays in place and he simply moves upwards through time, as you can see here. Allie, on the other hand, moves away from Bob and then comes back to meet him up here. These dashed lines I have represent a specific time for Bob. So like this is 1 second for Bob, 2 seconds, 3 seconds throughout space. So according to Bob, anything that happens on these dashed lines are simultaneous. They happen at the same time. All right. Now, I should give credit where credit is due. I am going to pretty much paraphrase this explanation from this YouTube video I watched from Minute Physics. I'm just paraphrasing it here. If you want more information, you should go check that out. So if we look at Allie's simultaneous lines, they are a bit more complicated. So remember, because Allie is moving, she's moving at near light speed. her sense of time is a bit skewed, compared to Bob's at least. Her lines for what's simultaneous are tilted, as you can see here. These purple dashed lines represent what she perceives as now. The exact angle, it depends on some math that we are not going to get into, but you should just know that they are tilted compared to Bob's. And this kind of lets us see the answer to the twin paradox. As you can see here, according to Allie, it only takes her 8 seconds, whereas Bob took 10. This matches up with what we understand, which is that Allie would return younger. However, as you can see right here, between this time and Bob, between about like 3.5 seconds to 6.5 seconds for Bob, all of this time for Bob was kind of compressed into just this one little instant where Allie turned around. So this kind of explains where the missing time went. This is still completely consistent. The interesting part is that this is still completely consistent with time dilation. As you can, if you just look at the time here, where Allie is taking 1, 2, 3, 4 seconds, she only sees a little bit over 3 seconds having passed for Bob. From her perspective, within a single reference frame, it is true that Bob is aging slower than she is. However, when she turned around, several seconds or years, several units of time passed for Bob, whereas they only passed in an instant for Allie. So this is kind of the solution to the twin paradox. Right? Yeah, so just this little swath of time was compressed into just a couple seconds for Allie when she turned around. So to recap, the solution to the twin paradox is this. Sorry. When Allie turned around, she was no longer in an inertial reference frame, and so therefore, special relativity and time dilation doesn't quite apply to her in the same way. This means that at the end of the day, Allie will return home younger than Bob. All right. The second paradox we're going to look at is the ladder barn paradox. Again, this is not technically a paradox. It's just easy to see how relativity can get twisted up. It's pretty similar to the twin paradox. The premise here is that you have a barn and you have a ladder that is longer than the barn. Obviously, the ladder cannot fit inside the barn. This barn has, by the way, it has a door on this end and also has a door on the back end. However, what happens when you try to run through this barn at near light speed? And if you'll just indulge me for a moment, these are supposed to represent the doors being open. I'm not a very good artist. Additionally, we're going to have an outside observer right here. And what he's going to try to do is that he's going to try and close the doors as soon as you're inside this barn. So the question is now, can both doors be closed? Will you ever be inside the barn? So again, the issue here is that there appears to be a conflict between reference frames. According to the outside observer, you move at near light speed, and therefore it is entirely possible for you to become length contracted enough to fit inside the barn, and so he can close the doors and everything's fine. However, according to you, the barn is what's moving. You're staying still, and so therefore the barn is what's length contracted, and if the ladder didn't fit in the barn before, it's definitely not going to fit now. So who's correct? So the solution to this is that the doors of the barn can indeed close. How? That depends on your perspective. So again, if we look at the point of view of the outside person, you have the barn, which is staying still, and the ladder, which is length contracted enough that it can fit inside the barn, and the doors can close at the same time. However, according to you, the ladder, and you, pretend you're here, is not length contracted, and the barn is actually what's going to move. And what you see is a bit weird. What you'd see is that you'd see the barn rushing towards you, and just before you pass through this door, it would close for a moment, then open again. And then by the time the barn had rushed all the way past you, just as you passed this front door here, it would close for a moment, and then open again. As you can see, the two doors of the barn did not close at the same time. How can this make sense? Well, the answer lies in what's called the relativity of simultaneity. So Relativity of simultaneity is just the idea that it's not always possible to determine whether two events are simultaneous. Like there's often no correct order of events. One moment. Right? So to take a more intuitive example, let's just imagine there's a person watching a storm, all right? So two lightning bolts strike, and if this person, let's just say they were perfectly between the two storms, the light from the lightning bolts reaches the person at the same time. They'd say the strikes were therefore simultaneous. However, let's now suppose that this person would be moving towards one of the storms. Now, because he was moving towards this storm, the light from this storm has less distance to cover, and so it reaches him first. And the light from this storm has a greater distance to cover, so it reaches him second. Now, according to him, the two lightning bolts were not simultaneous. And again, assuming that he was moving at a constant velocity and he wasn't accelerating, both of these reference frames are entirely valid. There's therefore no way to determine whether the two lightning bolts were at the same time or not. We can kind of apply the same concept to the ladder barn paradox. All right. So as we showed earlier, again, from the point of view of someone watching what happens, it's pretty simple. The ladder is simply length contracted enough to fit in the barn, and the two doors close simultaneously. This can be explained because the light from the two doors reaches the observer at the same time because the barn and the observer are both not moving. Relative to each other, at least. However, from your perspective, you see the back of the barn rushing towards you. And because the back of the barn is rushing towards you, the light from the back of the barn reaches you first. And therefore, you see the back door close, then open for you first. And similarly, the front of the barn is rushing away from you. So you see the light from the front of the barn closing and opening reaches you second. So you see that happen after you've already passed through. So to recap, both people will agree that the doors of the barn can close. What they will disagree on is whether they've closed at the same time or not, because of the relativity of simultaneity. Did the ladder fit in the barn? That depends on your perspective. And if we want to look at a space-time diagram again, we can also look at this for the ladder barn paradox. So here I've made two different space-time diagrams, one for the barn and one for the ladder. So over here, as you can see for the barn, it's not moving through space. It's only moving upwards through time. By the way, I've just erased these gaps in the space-time diagram to just kind of show when the doors will be open. It's technically just, going up and down, but it just helps to see when the doors will be open. All right. And these lines kind of represent how the ladder is moving. So remember, since the ladder is length contracted, it'll move upwards through time and it'll move through space. And at some point, it'll fit perfectly inside the barn. And just for an instant, both of the doors can be closed with the ladder still inside the barn. However, if you look at the point of view of the ladder, now it's the one that's not moving. And so its lines just kind of go straight up through time and they're not moving through space. And this time, the barn is what's moving through space and through time. So as you can see, the doors of the barn open and close at different times. And there is never one simultaneous time for the ladder where both of the doors are closed. So these space-time diagrams can also help determine what's quite going on. All right, and the last paradox we're going to look at for today is called the Einstein-Podolsky-Rosen paradox. And it's in a somewhat different vein than the other two, because this one's more of a history lesson than a discussion about length contraction and time dilation, but it still helps deal with some of the weird effects of relativity and quantum mechanics. But first, some background information will be necessary, so let's just take a quick detour to quantum mechanics. All right, so let's just suppose that we have this hypothetical particle, all right, and it can be in one of two states, red or blue. We haven't measured this particle yet, so we don't know which state it's in. However, traditional quantum mechanics theory states that it's not just that we don't know what state it's in, the particle literally is not in any one of the states. is in a superposition of both at the same time. And once we measure it, it'll collapse into one of the two states. This is kind of a good analogy for this is Schrodinger's cat, that thought experiment. Basically says that when the cat's in the box, it's both alive and dead. It's not that it's one of the two and you don't know. It's literally both alive and dead until you check in the box, and then it collapses into one of the two states. So in this case, as soon as we observe the particle, it will randomly collapse into one of the two states, either red or blue. And this collapse is completely random. It's impossible to determine which state it will collapse into. Quantum entanglement occurs when you have two particles, and they're said to be entangled when the collapse of one just automatically triggers the collapse of the other. All right, so for example, if we have these two particles and they're entangled, when we collapse this one, when we measure this one, let's just say it collapses to become red. This will automatically trigger the collapse of the second particle into blue, even though we have not measured this second particle. It'll just collapse anyway. Similarly, if we measure this particle and it collapses into blue, it will automatically trigger the collapse of this one to be red. And again, we didn't measure it, it just automatically was triggered. And the really weird thing about quantum entanglement, or I guess another weird thing, is that there's no distance limit. These two particles could be on opposite ends of the universe, and they could still be entangled. And you could still measure one, and the other one would collapse from the other end of the universe. So this led Einstein to realize that it's a bit of a paradox, right? Einstein, Podolsky, and Rosen. So they said this: let's suppose that we have two particles, they're entangled, and they're very far away. They're on opposite ends of the universe. And we measure one particle, and it collapses. We measure the other one immediately afterwards, and as expected, we find that it's already collapsed accordingly. This fits what we know about entanglement, which, the collapse of one causes the collapse of the other, and we can predict which one it is. If we know which state this one's in, we can then determine which states this one's in. However, since the collapse of the first particle was completely random, right, there was no way to predetermine whether it would collapse into red or blue. Since it was completely random, it must have transmitted some information about its collapse to its partner in order for it to collapse accordingly. This would require information to travel faster than light speed, which violates a fundamental rule of relativity. This kind of led to Einstein's famous rebuttal of quantum theory, which he famously called spooky action at a distance. So Einstein, Podolsky, and Rosen, they kind of developed their own solution to this paradox called the hidden variables hypothesis. This basically states that a particle's states are predetermined. They're basically rejecting traditional quantum theory, and they're saying that no, a quantum state is already predetermined. It's not in a superposition. It's already predetermined by some hidden variables that we don't know about. And since the states are already predetermined, there's no information being transferred between the two. A good analogy is to say that particles are like balls inside cardboard boxes, right? So if you have two cardboard boxes, you can't see inside of them, but you know that one of them contains a red ball and the other one must contain a blue ball, all right? So as soon as you look inside one of the boxes, and let's say it has a red ball, you immediately know that the other box must contain a blue ball. No information was transferred, nothing changed. It's just that by measuring the state of one box, you automatically knew the state of the other box, just because of the way it works. In reality, though, each box still only contained one ball. Nothing changed, nothing collapsed, everything was predetermined from the start. So if we connect this back to quantum theory and the hidden variables hypothesis, the boxes correspond with the two entangled particles and how they're always paired. You know that if one of the entangled particles collapsed to form into red, the other one must collapse into blue. You just don't know which one's which. However, by measuring one, you can instantly know what the other particle is, but it's not like any information was transferred. And this completely rejects quantum theory by saying that particles don't collapse as a result of measurement. But, quantum theory purists like Niels Bohr, they insisted that the collapse was entirely random and caused by the measurement. And so these two groups in physics kind of clashed for like decades after this. until this guy came along named John Stuart Bell. And in 1964, he developed a method to test the hidden variables hypothesis. And by doing so, when it was tested, the hidden variables hypothesis was actually found to be wrong. Quantum entanglement and the random collapse of particles really does occur. However, since the collapse of the states is completely random, no information was passed, which preserves relativity. And Bell's theorem had like a huge impact on the physics world, and there are many interpretations and implications of his theorem, which are still debated today. And in fact, many physicists around the world are still trying to unite relativity with quantum mechanics more thoroughly. It's one of the biggest, if not the biggest problem in all of physics today, which is trying to develop a theory of everything. So, in conclusion, the theory of relativity states that time and distance are relative, and all inertial reference frames are equally valid. Length contracts, and time moves slower for moving reference frames. And we also went over these three paradoxes that aren't really paradoxes. The twin paradox, which basically can be resolved by recognizing that one of the twins is in an accelerating reference frame, so special relativity doesn't apply. The Ladder-Barn paradox can be explained by the relativity of simultaneity, and the Einstein-Podolsky-Rosen paradox was resolved with Bell's theorem, and it still leads to questions about unifying quantum mechanics with relativity today. I'm trying to operate Zoom.
Cool. That was a really great talk. Does anyone have any questions for Tia? I guess I'll ask one then. What does it mean for like two events to be simultaneous inside a single reference frame? Like, let's say I'm using myself as a reference frame, and two events happen at the same time, but like maybe they're different distances from me, so I see them happen at different times. Like, how do you define simultaneity inside a reference frame?
That's a good question. So simultaneity basically means that any two events that occur at the same time. And it's true that you might not be able to maybe see them happen because they're at different distances from you. But because information, like it depends on what event happened, I guess. But if we're going to the lightning example, so we can just assume that it all travels at the speed of light, then even though you will see the lightning strikes at different times, if you take into account the different distances, then you'll be able to calculate the fact that they might have happened at the same time. It's just that you viewed them happening at different times. If that makes any sense. Yeah, I'm trying to think of like a good way to explain it.
I think your explanation is pretty good.
Yeah, so that's that.
I have a question too.
Mhm.
Okay, so you mentioned that two events can be simultaneous in some reference frames, and it depends on what reference frame you're talking about. But does the location of these two events also depend on the reference frame, or is that irrelevant?
Sorry, I couldn't really understand you. What I heard was you were asking is, does like the location and the distance of them have any effect on it? I think. Yeah. Okay. So yeah, this kind of connects back to how kind of time and space are linked. The relativity of simultaneity, it is connected to the fact that you might be at different distances and the fact that space might be a little bit different. I've heard this one explanation for simultaneity. Maybe it might make a bit more sense. Another way to think about it is that it's kind of like the counterpart to movement. So the same way movement, which is basically a change in position over time, is relative depending on which reference frame you're in. Like if in your reference frame, you aren't moving, the clouds are if you're in an airplane. But to somebody outside of the airplane, they would see the airplane is moving. The same way that movement is relative, simultaneity, which is just kind of how far apart things are in time based on how far they are in space, that's also relative in just kind of the same way. Time and space are really just two sides of the same coin in relativity. Does that help?
Cool.
Yeah, that's good. Thank you.
All right, if no one else has any questions, then thank you so much for giving your talk.